Hello, and welcome to the C-Motion tutorial on CalibrateDSX. This tutorial covers the correction of X-ray images and calculation of the 3D configuration of the X-ray and imaging equipment. This tutorial assumes that you have already created a subject file containing links to all of the data files collected during the capture session. This includes not only the X-ray image files, but also CT or MRI, as well as motion capture data if it was collected simultaneously with the X-ray images. This tutorial does not cover creation of the subject file, but let's take a quick look at it to highlight the components that are needed for calibration. The first component is a calibration device. In this case, we're using the big Lego cube designed by the X-ROM group at Brown University. It contains 64 tantalum beads embedded in a frame made of Lego bricks. It also has 4 uniquely shaped tokens to help identify the beads in the X-ray images. The XYZ locations of the beads and tokens must be defined here, along with the radii of the beads. The second component is a grid device, which defines the properties of the grid being used for distortion correction. This can be either a grid of beads or a grid of holes in a metal sheet. The spacing, size, and orientation of the beads or holes are defined here. If you're not performing distortion correction, you do not need to specify this device. The next component is displayed when you click on Calibration in the tree view. These are the distances between the X-ray sources and the image planes. They're usually measured with a tape measure or laser sight and should be measured to within a couple of millimeters for the best calibration results. Next, we have the X-ray images for the calibration trials. For cameras 1 and 2, we specify the raw files for the white images for non-uniformity correction, the grid images for distortion correction, and the images of the calibration object for the calculation of the 3D configuration. If you do not want to perform non-uniformity or distortion correction, you can leave those file paths empty. CalibrateDSX will give you a warning that these files are missing, but you can then proceed with correction while bypassing non-uniformity or distortion correction. Finally, we have the image data for the 2 subject trials, standing and walking. Now let's launch CalibrateDSX to begin the calibration process. We'll start by opening the Calibration Parameters widget and the Image Processing widget, as both of these are needed to process the calibration images. Then we select a session and a configuration that we want to start with. Once the configuration is selected, CalibrateDSX scans the images in the calibration trials to determine their XY dimensions. It is at this point, before any trials are selected for correction, that we need to specify the final dimensions of the corrected images. Determining the optimal resolution of the corrected images is beyond the scope of this tutorial, but it depends on several factors, including the bones being tracked and the resolution of the CT or MR images used to construct the 3D bone models. In any case, the final dimensions of the corrected images must be specified at the start of the correction process, because all of the images in both calibration trials and motion trials must have the same dimensions. For this tutorial, we'll reduce the resolution by a factor of 2, so we'll enter 880 for both the X and Y dimensions. Now we can select the intensity trial. This dialog tells us that the trial has not yet been corrected. We're going to choose to correct it and save the resulting subject file to a new name. I like to keep a copy of the original subject file in case I want to go back later and repeat the calibration process. Correction of intensity images involves removing outlier frames, that is, frames whose average intensity is more than 2 standard deviations from the mean intensity of the entire trial, and then averaging the remaining frames into a single frame. I'll just add a 2 to the name and save it. The white images in this dataset are not ideal, but they still provide some benefit in non-uniformity correction. Ideally, no pixels of the images should be saturated at maximum intensity, as many in these images are. The purpose of white images is to show local variations in intensity that occur not only around the edges of the viewing circle, but also in the interior. Gray image might be a better term, as we recommend that the average intensity across the image be about 75% of maximum. It is not a problem if portions of a white image are dimmer than portions of an image being corrected. For non-uniformity correction, the output image is the white image minus the input image performed in log space, and the result is shifted uniformly to the high end of the intensity range to make the corrected image as bright as possible. Our goal with the white images is to specify a threshold for each view that masks out the background. When non-uniformity correcting the other trials, pixels in this masked area will be set to 0. We start by turning on Show Processed X-rays in the Image Processing widget. Then we can adjust the white threshold view 1 parameter to create the mask. Too low a value doesn't remove all of the background, and too high a value removes some of the viewing area. For this image, there's a wide range of values that work well. We can even leave the threshold at its default value of 0.3. For camera 2, we adjust the white threshold view 2 parameter. The default value of 0.3 works well here too. Now that we're done with the intensity trial, we can load the grid trial. We'll choose the option to correct the grid images and save the subject to the new file. Correction of grid images involves removing outliers and then non-uniformity correcting the remaining frames. Our goal with the grid images is to specify parameters that separate each grid hole from the background and from its neighbors. Turning on Show Processed X-rays reveals this cyan red color coding. A cyan group of pixels means the group is the right size for being a valid grid point. Red means the pixel group is either too big or too small. There are threshold parameters for separating the grid holes, and size parameters for specifying how big the holes should be. By zooming in with the mouse wheel, we see that the threshold is too low to distinguish the individual holes. As we increase Grid Bead Threshold View 1, the regions turn cyan as they are separated. Doing the same for camera 2 with Grid Bead Threshold View 2 gives us this. Zooming in again, we can see that this hole is still connected, so we increase the threshold a little more to separate it. And we can do the same thing for camera 2, increasing the threshold slightly to separate a grid hole. Now we need to decide how many of the partial grid holes at the edges we want to include in the distortion correction process. If the holes consist of only a few pixels, then they won't give an accurate representation of where the center of the hole is. We can adjust the size range of the valid grid holes to remove the partial ones, but if we go too far, then we start to lose some good ones. In any case, if the bones you'll be tracking are not in these regions with the partial grid holes, then it's probably not important which ones you include or exclude. This region here is not a concern. If a missing grid hole has at least 2 valid neighbors, then its position can be interpolated, so all 3 of these missing ones will be filled in when the displacement map is created from the grid of holes. A final note about the grid trial: the current version of the software processes only the first frame, so you don't have to check the threshold values on the other frames. We can now load the calibration trial, again choosing the option to correct the images and save the subject file. The calibration images are corrected by first applying non-uniformity correction, then distortion correction. Here are the corrected images. If we have any concerns about distortion correction working properly, we can examine what are called the grid check images. Every time CalibrateDSX distortion corrects a trial, it also distortion corrects the grid images themselves. You can view these by pressing the G key in either view and verify that the grid lines are all straight without any missing segments. To compute the 3D configuration, we first need to digitize the bead locations in the calibration object. Opening the calibration widget, we see the 64 beads with the 4 tokens at the bottom of the list. Because it's nearly impossible to identify the beads themselves, we're going to manually identify only the 4 tokens. I select the pyramid token by clicking on its name. Then in the images, I can control-click on the pyramid in each view. After I've defined it in both views, the widget auto-advances to the next undefined token, the iframe. In this way, I can quickly define all 4 tokens. Now I can instruct CalibrateDSX to use these tokens to calculate the locations of all 64 beads and digitize them on the images. This is done with the Predict POI Locations command. The software calculates a crude 3D configuration from the tokens, then projects the 64 beads onto the images. The area around each projected point is searched for a circular region representing the bead. Then its weighted center is marked as the bead location. Now that the beads have been identified, we can remove the tokens, since they are less accurate than the beads for calibration. At this point, we could examine the bead locations carefully, trying to fill in those that are missing or misidentified. But an easier way to do this is just to go ahead and compute the 3D configuration and look at the residuals. We do this with the Compute 3D Configuration command in the Tools menu. Using whatever beads are identified in each view, a DLT algorithm computes the 3D configuration for the view. The residuals are shown in a table. For each bead, the total residual in millimeters squared is shown, as well as the X and Y components. Residuals that are more than 1 standard deviation above the mean are colored red. We can leave this dialog open as we use the values to address the high residuals. We could look carefully at the bad beads and try to fix them, but since we have so many good beads available, we could also just remove the bad ones. So we'll remove 34 and 53 from view 1, and 7 and 43 from view 2. 7 is problematic because 2 beads overlap. And it looks like the iframe is interfering with the weighted center calculation of 43. Let's zoom in a little to get a better look. Now let's close the dialog, reset the view, and recompute the 3D configuration. We still see some red numbers because there will almost always be residuals more than a standard deviation above the mean, but their values are reasonably low. And the total residuals for both views are quite good, especially considering the number of beads in the calculations. Although the current set of beads is sufficient for calculating the configuration, I'll show the process for manually digitizing beads in case it's needed in other instances. Let's start by turning on the display of what's called the Perfect Calibration Beads. This command is similar to Predict POI Locations, but it displays X's at the projected locations instead of calculating their weighted centers. It shows you where the beads would be if the residuals were exactly 0. Now let's go back to beads 34 and 53, which we removed earlier, and manually digitize them. We can see the bead 34 has a purple label, so it's the one in the image with the purple X. Now let's turn off the X's and select bead 34 in the table. The cursor changes to a circle inside a square with a 34 next to it. The cyan circle represents the expected size of the bead, given its radius specified in the subject file and the pixel size of the image. The yellow square is the search box, the region of the image that will be searched for the pixel that best represents the center of a light region surrounded by dark pixels. The bead finder algorithm works best if the circle is about the same size as the bead and the box is not large enough to encompass more than one bead. To make the circle smaller, we go to the Calibration Parameters widget and decrease the POI scale from 1 to 0.8. And to make the box smaller, we decrease the click search factor from 1.5 to 1. Now they are a better match for the beads in this image. To show how the weighted center algorithm works, I'll click away from the bead, but close enough that the actual center is inside the search box. And we can see that it did a decent job of finding the bead center. But the algorithm was affected slightly by the pixels of bead 53. To be even more precise when working with overlapping beads, I can zoom in, center the cursor over the bead, and press Ctrl while clicking. This will bypass the weighted center algorithm and enter the exact coordinates that I clicked on. With bead 34 now digitized, its pixels are masked out when digitizing subsequent beads, so I can select bead 53 and simply click near it to find the weighted center. Now let's calculate the configuration again and see the difference. The total residual for view 1 is slightly higher, with bead 53 one of the higher values, but still not that bad. For this tutorial, we'll just leave both beads in the calculations. The last step, which is optional, is to propagate the bead locations from frame 1 to the other 10 frames of the calibration trial. It's sometimes helpful to average the bead locations over several frames to minimize noise from slight variations in intensity. We do that with the Propagate POIs command, and it operates over the range of frames specified by the tracking slider. If you look closely, you can see some of the bead centers move by a pixel or so as I scroll through the frames. If we now calculate the configuration one last time, we can see that the residuals are slightly lower for both views. Once we're happy with the configuration, we want to save the bead locations to text files in case we want to revisit the calculations later. This is done with the Save 2D POI Locations command, saving a text file for each view. Then we save the subject file with these file links and the configuration parameters for each view. For this configuration, we're now done with calibration. The only thing left to do is correct the other trials in it, the standing and walking trials. Before correcting these subject trials, you'll need to determine the appropriate Gaussian smoothing parameters. Smoothing is applied to the full resolution images before they are resampled to the specified final image size. Smoothing is generally recommended, but the optimal settings depend heavily on the image quality and the detail on the bones being tracked. For this tutorial, we'll leave smoothing turned off. Then we select the Correct All Trials in Configuration command. The software will correct every trial in the configuration that has not already been corrected. Some of these dialogues showing various steps of the process will display only briefly with a fast enough computer. Once it's done, we can preview the standing trial, scrolling through the frames to make sure everything looks good. Then we do the same with the walking trial. And we save the subject file now that we're done with the left leg configuration. If there were other configurations or sessions for this subject, we would then move on and process those. This completes the CalibrateDSX tutorial. Thank you for watching.